The fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
All right, hello everybody. Thanks very much for coming to my talk about contracts for C++. My name is Timur Doumler. It's actually the 5th time I'm giving this talk, but it keeps changing. And this time it evolved quite significantly from the last version I gave, because things keep evolving and progressing. And so this is a substantially reworked version of the talk. What is this about? It's about a proposal to add a new feature to C++ called contract assertions, which allow you to put precondition and postcondition assertions on a function declaration to express the preconditions and postconditions of that function. So they look like that, pre and post. They're collectively called function contract assertions because they're contract assertions that go on a function. And then there's a third kind of contract assertion, which is called assertion statement, which is contract assert, which can go into the body of a function. And we would really have liked to call this just assert, but unfortunately that clashes with the existing assert marker. So we had to come up with a different keyword, and contract assert is the keyword we landed on. All of the stuff is a proposal for C++, which is targeting C++ 26. It's not formally voted into the C++ 26 working draft yet, but I very much hope you're going to get there. You can always read the latest version of this proposal if you put into your browser wg21.link/p2900. which is the paper number for this proposal. I'm going to have other paper numbers in this talk as well, and you can access all of them by typing wg21.link/paper number. So this proposal has a bunch of names in it, a bunch of people who are working on it. And we are participating in ST21, which is the contract study group on the standardization committee, which I am the co-chair of. So we have been working in this study group on this proposal for quite a few years now. We have now actually forwarded a version of this proposal to the next level on the committee, which is the Library Evolution and Language Evolution study group, and it's being design reviewed there now. So this is kind of what's happening over the next couple of meetings. And then hopefully it will be approved and progress through plenary and hopefully then into the actual standard. So one question that I got asked a lot, including this week, is why did it take so long? Or why is it still taking so long? Because we still don't quite have contracts in C++. We're not quite done yet. And yes, indeed, it took quite a long time. Design by contract and contract-based programming was invented by Bertrand Meyer in the 80s. In 86, his programming language Eiffel was published, which was the first programming language that supported contracts natively. And that was almost 4 decades ago, right? So a lot of time has passed. Since then, there have been other programming languages that are implementing contracts today, including the D programming language, which came out in 2001 and came with contract support out of the box. And then later in 2012, the Ada programming language also got contract support. Actually, it turns out that the history of contracts in C++ is longer than the history of contracts in Ada, because the first proposal to add contracts in C++ is actually from 2004. So that was shortly after D was released. It was heavily based on the way contracts do work in D, so it was very, very heavily based on the D language, that proposal. But that is also 20 years ago, so we have 2 decades of history of just trying to add contract support to the C++ programming language. If you look at that history, so that proposal came out in 2004. The main author was a person named Thorsten Ottesen. That was considered for a few years. I think it was even considered to be included in C++ 11, but that didn't work out. That proposal got abandoned. There was then later a second phase. There was a second proposal by John Lakos and other people from Bloomberg based on their BDE library. So it was a macro-based solution to add contract support. So that proposal came out in 2013, went through a bunch of revisions as well, and in the end failed in plenary in the committee because people didn't quite agree that that was the right design direction. But around the time when that happened, there were quite a few other people who were working on this and wrote alternative proposals where things were kind of specified differently. Some of them are Gabriel Dos Reis, José Daniel Garcia, Alistair Meredith, Walter Brown. I wanted to point out that paper. That was the first paper published that suggested to use the double square brackets as a syntax, which was that ended up the idea at the time in a merged proposal where all of these people got together and agreed on a proposal. So that was the so-called merged proposal or attribute-like proposal because it was using the double square bracket syntax. Some of you might be familiar with that. Some people now call it the C++2A contracts proposal because it was targeting C++20 and actually was voted into the C++20 working draft approved by plenary in 2018. But then after it was already in a working draft, some problems with the specification surfaced, which then led the committee to decide that that wasn't actually ready for standardization. And then in a dramatic move in summer 2019 at a committee meeting in Cologne, that version of contracts was removed again from the C++20 working draft. At that meeting, SG21, the context study group, was founded to kind of pick up the pieces and try and come up with a contracts proposal that actually will gain the consensus of the committee and hopefully make the community happy as well. So SG21 has been working on this since 2019. So this is kind of the fourth phase, the fourth proposal. Last year, we actually published a first version of this proposal that we have on the table today. We call it the contracts MVP proposal because it's a minimum viable product. It doesn't contain every feature that you might possibly want from contracts. It contains a subset that we think is viable and useful and is designed to be extended later to address the use cases it does not currently address yet. So that proposal in February this year was forwarded to the Library Evolution Working Group for design review. And that's where it is right now. And we are a bit less than a year away, I believe, from feature freeze for C++26. So as we will see, there's a few things to iron out still, but I'm an optimist. I think we have enough time to do that and to get this feature hopefully into C++26 before feature freeze. But why did it take so long? Why did it take 20 years to come up with this proposal? Well, in order to understand that, we need to understand what contracts are. So this is just kind of the original definition, I guess, from the 80s. Contracts are an approach to software design to define formal, precise, and verifiable interface specifications for software components, extending the ORDIN definition with preconditions, postconditions, and invariants, and they're called contracts, in accordance with the conceptual metaphor with the conditions and obligations of business contracts. So that's kind of the dry kind of definition, basically the way it was conceived in the 80s and kind of how it is still understood today. We see three things there: preconditions, postconditions, and invariants. And in fact, Eiffel, and Ada support all three of them. We will only talk about preconditions and postconditions in this talk because invariants in C++, making them work in C++, is a little bit more tricky. So we don't quite know how to do that yet. So that's one of those features that we decided we're going to do later, not in the first version, but in a later version once we understand how to specify them correctly. So we're not doing invariants just yet. We're doing preconditions and postconditions. A precondition is a condition on calling a function at the time when you call a function on the state of the program, which typically includes the parameters you pass in, but could also be other aspects of the state of the program. So a program call can have a precondition. And a function can also have a postcondition, which is a condition on either the value that the function returns or the state of the program at the time when the function returns, right? And these contracts, they do exist today already, right? So that's something that we already have. Functions all over our C++ code have preconditions and postconditions today. Typically, they are realized as so-called plain language contracts, so they're written out in English. Or some other human-readable language to reflect the understanding of how the program is specified and how the function is specified. For example, operate a square bracket. Typical example has a precondition that the index is not out of bounds. Right? So that's a precondition. That's a contract. And often you would write a code comment or some other form of documentation to reflect that so that the person using this function knows that they shouldn't be calling it out of contract with an index that's not smaller than size. The C++ standard itself is also full of preconditions and postconditions. Contracts, for example, this is the specification of the same function for a vector, I believe, or array in the C++ standard. The standard also explains what a precondition and a postcondition is. It says, for example, preconditions in the standard are the conditions that the function assumes to hold whenever it is called. Violation of any precondition results in undefined behavior. As you're going to see later, that is actually a particular contract semantic, one of several possible contract semantics, the assume semantic, which is the status quo today for preconditions in the standard library. So we have contracts today, right? We can express these things in this way in English. But what we really want to do is you want to express contracts in C++ code, right? Because that gives us a lot of benefits, a lot of things we can do with them. This is kind of the whole point, express contracts in code, which leads us to contract assertions. And that is the feature that lets us do that. So what are these contract assertions for? And I guess that is going to bring us closer to the answer to the question, why did it take so long? So one of the early kind of works that we did in SG21 is this paper from 2020, is we collected use cases for contracts. We asked around in the committee and outside of it, like what would you like to use contracts for? If you were to specify a feature that adds contract assertions to language, what would you want to use it for? How would you want to use it? We compiled a lot of use cases. Guess how many we identified? Anybody wants to guess a number? How many different use cases?
195.
Yeah, 196. Almost. I think I counted them once. I counted 196. Then other time I counted 197. So it's like something around that. So a lot of things that people want to use contracts for, including all of these, right? So there's a lot of stuff in here. Like some people want to use them for correctness or for verification, for safety and security, for runtime checks, for performance and optimization. So there's also kind of tension between these things, right? So it appears that this could be a feature that satisfies all of those things, except you can't really satisfy all of those things in a single feature. If you wanted to cover all of these use cases with a single language feature, it would be so complicated that you would never be done specifying and implementing. And you would be trying to do something like this egg-laying wool milk pig, which is a concept from German folklore, which kind of does everything. It gives milk and eggs and wool and everything and meat all at the same time, except that such an animal, of course, isn't really viable. So we don't know how to specify a feature that can do all of these things simultaneously. So we have to descale, right? We have to limit ourselves to certain use cases at the expense of others, which we're going to add later, ideally without cutting off the kind of evolution direction towards those other features. And that brings us to the next problem, which is the other answer to the question, why did it take so long? As soon as you realize that you can't do this, you end up in this situation where everybody wants to pull the cart into their direction and wants to get their feature and wants the feature to be designed according to their mental model of what contracts are. And that is something that took us quite a while to overcome. It is a difficult exercise in consensus building to get very smart people to pull in one direction rather than in different directions. But I think we've done a great job over the last few years, and we actually kind of agreed on in which direction we want to pull this cart for, at least for C++26, which culminated in this proposal that we have now, P2900. So the question we are asking today is, what are P2900 contracts for? So they're not for all of these things that you saw a few slides ago. They might be for all of those things later, but right now, they are for a subset of those things. And so I tried to formulate an answer to this question myself, and I ended up with something like this. So this was kind of my answer off the top of my head to the question what P2900 contracts are for. They enhance a C++ program with configurable checks of its correctness. So it's about correctness, thereby helping to diagnose and fix bugs, right? So it is all about fixing bugs. Sorry, where are we? Yeah, here we go. You have configurable checks of this correctness, right? So you can configure these checks. And you do that in order to fix bugs, and you can do that across API boundaries. Okay, so that's kind of my take on it. But it felt to me that, okay, I am maybe slightly missing some aspects of it. There's more going on in this proposal. So I asked two people who are co-authors also on this proposal, whom I worked quite closely with to get this over the finish line. Lisa Lippincott, who's in the back of the room there, and Joshua Brown, who is not here. What is your take on why are we doing this? What is this feature for? So this is Lisa's answer. I hope, Lisa, it's okay that I put this on the slide here. This is what you told me. P2900 contracts allow the programmer to express expectations about program state and optionally verify that those expectations are met. So it's a slightly shorter, kind of more elegant, more kind of boil down to the essence definition. It talks about expectations about program state. Lisa said, oh, you talk about bugs, and this is all very negative. This is a kind of more helpful way to describe this. Like we have expectations what the program state should be, and we can verify whether those are met. And a word here that she added that I didn't have in my version of this is optionally. So not only can we configure these checks, but we can actually turn them off. And that's a really, really important aspect of what P2P contexts are. Well, I saw this and I was like, oh, okay, so this is a very elegant definition, but it's also, again, missing maybe a few things. So I asked Josh what his take on this is. He's another co-author on this paper. And that was his answer, which was a lot longer than Lisa's or mine. So Josh said that, in his opinion, P2P contracts allow the programmer to specify states that are considered incorrect at certain points in a C++ program, particularly when calling and returning from functions, and then manage how such defects can be detected and mitigated in a portable and scalable fashion during program evaluation. And I think that's actually a very good summary of what this proposal is about. So it adds a few aspects here that are missing from the other two. It's talking about particularly when calling and returning from functions. So that's this kind of precondition, postcondition aspect of functions that we can express now. It talks about mitigating defects. So not only can you detect that a contract violation has happened, but you can also do something about it. It is meant to be portable and scalable. So that's another really important aspect. If you have a code base with 100 million lines of code in a big tech company, you're supposed to be able to use this feature at that scale, right? And another really, really important aspect of what we're doing is that these checks happen during program evaluation. And kind of that's the core of the design here. And we're going to talk about this later, but I think this is, my favorite version of describing what this proposal is about. Sorry, Lisa. So let's look at some code. So let's look again at yeah, there's a question?
Forgive me. When you say during program evaluation, you're talking about compile time?
We're going to talk about that later. But during program evaluation means while your program is running, while code is executing. We're going to talk about that. It includes runtime and compile time. Because you can evaluate constant expressions at compile time. So that's also program evaluation. We're going to talk about that later. OK, so we have operator square bracket, which is our kind of typical maybe example of a simple function with an obvious precondition. That could be vector or span or array or something like this. It doesn't really matter. And so depending on how you implement this, violating the precondition might have different consequences. For example, if you implement it in this straightforward way, that you kind of index into an underlying array that contains your data, and then you violate the precondition here, then you get UB, right? So you get either maybe a security vulnerability where somebody can access memory that they're not supposed to access, or maybe the compiler can say, oh, I know this can never happen, and optimize your program in really weird ways and so that it breaks in very non-obvious ways, and other bad things that can happen here. And but all of these things mean that at the end of the day, your program is not going to be correct and probably also not going to be secure or safe, which is not good, we want to do something about that. So what can we do about that? We can replace the function with a function that doesn't have preconditions, right? So we can use operator at, for example, which will check the index, and if it's out of bounds, throw an exception. Right? So this is an obvious way to not have any safety and security problems here, and to have a correct program, because you get this exception, you can do something about this programmatically. If you're not a fan of exceptions, you can write your own version of this, which checks the whether the index is in bounds within range, and then if it isn't, do something else, which is, for example, terminate or whatever is appropriate for your situation. So you can do that today, and at this point, if you've done this, you've solved the safety and security problem, right? There is no undefined behavior here or anything. This is a safe and secure version of this function. I mean, depending, again, on the system, right? If it's not safe in your environment to terminate, you might want to do something else. But there's no UB here, right? So you solve the safety and security problem. At this point, you're done. But maybe that's not quite enough, because we're in C++, right? So we also care about performance. So maybe there are situations where you want to do this for safety, but there's other situations where you want to not pay for the bounds check because you want to be maximally performant. And maybe you don't care so much about correctness in that context, or more likely, you know that the bounds check is not going to be violated because of some other aspect of it. For example, you've tested the program very extensively. You have very good unit test coverage. So you know that this is fine. You don't want to pay for this check. So you want to disable it in certain scenarios, or maybe do something else depending on what you're doing and how you're deploying your program. And this is exactly where contract assertions come in. So you can, instead of doing what we saw on the previous slide, you can add a precondition assertion, and thereby you can express that there is an expectation that this operator is not going to be called out of bounds, but you're not saying in code what should happen if that's violated or how this is checked. So what you're doing is you're separating this decision from the code you wrote. You're just expressing what would constitute a correct program, but you're not saying how this is supposed to be verified or mitigated if that's not the case. So if you talk about just kind of conceptually contracts, there's always this kind of two sides of it. There's a caller and a callee when we talk about pre and post conditions, right? So the caller reads the contract and needs to ensure that when they call the function, they call it correctly, the preconditions are met. Function returns, they can rely on the post conditions being met. And the flip side of that is the callee, the implementer of the function. They write the contract assertion, and they can expect that the preconditions are met, and they need to ensure that the post conditions are met when they're implementing the function. But P2100 contracts add a third role here, which is a third person. And all of this can be one person, but it can also be three different people. And this role is the role of the person who actually compiles the program, right? And so the person who compiles the program, they enable or disable the checks. They configure what should happen when these checks fail. And so that is something that is now separate from the code that either the callee or caller see. And this is really the salient, the most important aspect of what you can do with P2100 contracts that you can't do with any feature today. Except, I think there actually is a feature in the language today that can do exactly this already. Can somebody tell me what that feature is? Assert. Of course, you can do exactly what I described in the last slide already today with assert, the assert macro, the good old assert macro. It does exactly that. You put an assert in there, you're not saying what's going to happen, but the person compiling the program can enable or disable and debug and then decide, do I want to check the assert or not, and do I want to terminate if that fails or not? So that's great, and we've been using this for decades now. But assert is not enough. It's not quite what we need in a lot of cases. It's just not flexible enough. It's not usable enough. So this gives us another answer to the question, what are P2100 contracts actually for? And it turns out that P2100 contracts provide a superior replacement for cassert and similar macros. And that's another way of looking at what the purpose of this proposal is. Turns out there's quite a few problems with assert or other macro-based solutions. One of them is that they're macros, and P2100 contracts are not. If you have a comma somewhere in a macro, it thinks that that's the start of the next macro argument, and then your parser is going to break horribly because it's not actually parsing it as proper C++ code. It doesn't know about curly brackets, it doesn't know about angly brackets, etc., etc. P2100 contracts are not macros, so this is going to compile like a normal C++ expression there with contract assert and also with pre and post. Another problem with macros is, well, if you compile the same function in one translation unit with ndebug off and in another translation unit with ndebug on, then you have an ODR violation. You have two different definitions of the same function in the same program, so that's not going to probably go very well. With P2100 contracts, you don't have that problem. You have a very similar way of enabling and disabling contract assertions. One way of doing this is also with a compiler flag. But if you link them together, you're not going to get an ODR violation because it's a language feature, it's not just macros. A third problem with macros is bit rot. If you have an assertion that's disabled and there's something in there that isn't actually valid code, it's fine because it's just textually removed until you turn off ndebug, and then everything horribly breaks. With P2100 contracts, that's not going to happen, even if contracts are disabled. Contract semantics are ignored. We're going to talk about semantics in a minute. It will still be parsed as a proper C++ expression and ODR used and all of that. Even if there's no runtime check at all, it's still going to be parsed as C++ code, so you can't get into this bit rot problem. Another thing that you can't really do with macros is you can't put them on declarations, right? You only can put macros into a function body, but you kind of really want to put them on declarations because you want to tell the user, maybe in a header file, these are the pre and post conditions of the function, and the user shouldn't have to read the implementation in order to see that. And well, with P900 contracts, you can put pre and post on a declaration. That's the whole point of pre and post, that you put them on a function declaration. You can optionally also put them on subsequent declarations. For example, a definition. You can repeat the pre there. It's optional. You don't have to repeat it, but you can. If you do, it has to be the same precondition sequence or postcondition sequence. But it has to be on that first declaration, right? So if you have declaration and definition kind of separate in your code, then the pre and post conditions need to be written out on the first declaration. Another thing you cannot do with macros, you can do with our proposal, which is really, really cool, is in a post condition, very often you want to talk about the return value of a function. And you can do that directly. We have a syntax for that. You can put any identifier there, like R, but you can name it X or ret or whatever. And then colon, and then your expression, and then that name refers to the object that the function returns. And it's not a reference, it's not a copy, it's more like structured bindings where you introduce kind of identifiers that refer to the members of this object that you have declared there. So this is kind of mental model-wise very similar. You introduce a name for an object that is already defined. It is the thing that the function returns, but doesn't have a name otherwise. But now you give it a name. And you can't really do that with macros. You can emulate it to a certain degree, but if you have if you return the result of an expression, it doesn't really work. For example, this works in all cases, and it even works when you are returning a non-copyable and non-movable object, and you rely on guaranteed copy elision to do that. I think we got that since cplusplus 17, if I'm not mistaken. You can return, for example, a stored atomic, which you can't move it, you can't copy it, but you can return it. That's fine. And the cool thing is that this return value thing here in the post condition will refer to actually that object that you have initialized there. So that is really, really cool. It doesn't refer to anything else because there is no other object here. We make this work by defining when and how exactly pre and post are evaluated. So this is the spec. Precondition assertions are evaluated after the initialization of function parameters, which is important. You can talk about them in that expression, but before you start evaluating the function body. That hopefully makes sense. Postconditions is slightly more interesting. They are evaluated after the result object value has been initialized. This is why this thing on the previous slide works. And after local automatic variables have been destroyed, but before you destroy the parameters. So you can talk about the parameters in the postcondition. So that's why this works, right? So by the time the postcondition of F is evaluated, the stored atomic int A in main has already been initialized. So this is really cool. This just works. Another thing you can do is you can refer to private variables in pre and post. They're kind of on the declaration, but they're also connected to the definition in the same way that contract is both an aspect of the interface of a function and also the implementation of functions. You can talk about private variables there. There's name lookup rules that make sure that that works. You can have an arbitrary number of pre and post. You can even swap them around. You can write the post first and then the pre. That doesn't matter, it all works. One tricky thing here, so this is a clamp function. I think hopefully everybody's familiar with what a clamp function does. It takes a value, min, max, and then it makes sure that it clamps the value to a value within that range. So these are the pre and post conditions of that function, so that they kind of describe what it does. And we are referring to parameters here in the post condition. And whenever you're referring to parameters in a post condition, they need to be declared const on every declaration of the function. Because otherwise, if you didn't have that rule, what you could do is you could do something very evil. You can just set all of them to 0 and return 0, which is completely nonsensical. But the pre and post conditions would be satisfied, right? So in order to write meaningful post conditions for like non-reference parameters, you need to be able to reason about the fact that when your function is called, these parameters have not been modified by the point you're done with the function and you get to the post conditions. So they have to be declared const here in order to refer to them. Is there a question?
Yeah, like because in C++, I believe in C++, like const on a value types for function parameter does not matter. It's not part of the signature.
Yes, it is not part of the function type. So
Yeah,
if you omit the const, you're still declaring the same function, but your postconditions are not going to compile if you omit the const. It has nothing to do with the type of the function or anything
I mean,
like that.
in the implementation, it may not be const. Right.
I have a lot of slides to get through. Let's have that discussion afterwards, because it might eat up a lot of time if we get into the weeds of this. So I suggest to talk about this afterwards, because I have a lot more slides. So basically, this won't compile unless you put the const in there, and we can have a conversation later about how to implement this. And let's do that. All right, so now we know how to spell these things, when they compile or when they don't compile, like when they're evaluated, like what the semantics are of this expression. But what happens when that expression evaluates to false? What happens when the contract check fails? So with cassert or other assertion macros, with other assertion macros, if you implement them, you can decide what they do. But with cassert specifically, if you turn them on and they fail, then what happens is that it logs a message and terminates, right? That's what happens. And you don't really have any other option there. With pre or post or contract assert, something slightly different happens. It calls the so-called contract violation handler, which is a special function that we define. The implementation provides a default definition of that contract violation handler called the default contract violation handler. And the default contract violation handler logs a message and terminates. So actually, the observable default behavior is exactly the same as for macro assert. But the new thing here is that you can configure that. So you can't do that with cassert. You can do that with custom assertion macros, right? If you have your own, oops, what's going on here? Sorry, my watch is doing weird stuff. How do I, whatever. So if you have your own custom assertion macro, you can define it in whichever way you want. You can do whatever you want. You can control it with whatever flags you want to define. That's all fine. But the problem with that is that it doesn't work across different components, right? So one library might define their own assertion macros, and you're using another library like Boost or whatever, and it has different assertion macros. And there's not really any way to handle them all program-wide in the same way. And this is what P2100 contracts give you. They give you one contract violation handler for the entire program. And every assertion, no matter which library that you linked with it came from, will end up in the same contract violation handler. So that is a really, really powerful approach. The way it's specified is that it's a replaceable function, or maybe a more real computers term for it is a weak symbol. So this is the way operator new and operator delete are specified today as well. It's kind of the same mechanism. There is a definition there, but you can just define your own, and then it's going to be replaced at link time, and it's going to call into your own version of that. So all you have to do in order to get that is you have to define a function with this exact name and signature, and then link that in, right? So at the point you have a library, you don't have to know what that is. You only have to decide what that is at the point where you link the final program, which is important because you don't want to make this you don't want to make the violation handler substitutable at runtime, because there's a lot of security issues related with that. So it's a link time thing, it's not a runtime thing. At runtime, it's set in stone what the violation handler is. You can define your own, and you can do whatever you want in it. Like, it gets this one parameter here, which is the contract violation object, which tells you what went wrong and how. And you can log, for example. You can trigger a breakpoint. That's useful when you have a debugger. That's another feature we're going to get in CPlusplus 26. You can do more interesting stuff. You can spin or put the thread to sleep or whatever until a debugger is attached, and then you can trigger a breakpoint. This is something that custom assertion macros do today. I've seen this in code bases. You can print a stack trace. You can really do whatever. You can also print a stack trace or do whatever, and then fall back to the default violation handler afterwards. So there's a special function, invoke default contract violation handler, which will call the default one, which you can optionally invoke from your custom one. And that's going to do the log and terminate thing, if that's what you want. And interestingly, you can also throw an exception from the contract violation handler. And that will let you basically try and recover, rewind. Oh, something went wrong. We have a bug here, but we can't terminate. We have to do something else. We have to recover. So you have to keep running. So you can unwind the stack and try and doing something else. So you can even implement your own recovery strategy here. You shouldn't use this for error handling. Contracts are not for error handling. They're for detecting bugs. But sometimes you can't just terminate everything if you hit a bug. And that's where this comes in handy. In order to use this, of course, you need to follow what is known as the Lakos rule. You shouldn't put no except on a function that has preconditions, because otherwise it's not going to unwind the stack, it's going to terminate, which is exactly the thing that you try to avoid. So you don't put no except on a function, even if you know it's never going to throw an exception if you call it correctly. But it might throw an exception if you call it incorrectly, and that's why you don't put no except on it. And that's why, for example, the vector operator square bracket doesn't have no except on it, even though it's not going to throw an exception if everything's okay, right? So if you want to use this feature, you need to follow this rule. We had quite a few discussions on the committee about whether that's really the right approach. People said, oh, but now suddenly all my assertions can throw an exception, and I don't even know it because it's only a decision that you make at link time. I don't even know if this is going to happen with my code. I never wrote this library with exceptions in mind. Oh my God. Yes, well, in this case, don't use this feature, or if you have a library, you can document that it doesn't support this, right? That's all fine. But we decided that the right trade-off is still to provide this feature, and if you don't need it, you just don't use it, or you don't support it, that's fine. I think throwing violation handlers is kind of a niche use case. It's probably not what most people are going to do, but we still need to provide it because it has important use cases. So if you don't need it, don't use it, but it's there. So we have this little bit of library API. This is actually all the library API we're proposing. It's just this contract violation object there that tells you a little bit about the violation, so you can program your violation handler, and then this other function at the end to call the default violation handler. So there's just this class here, this struct with 5 members. That's all there is. There's a member function location, which gives you a source location where the violation happened. There's a member function called comment, which gives you a textual representation of the expression that failed. There's detection mode, which is a little enum that tells you how the predicate failed to evaluate to true. It might have evaluated to false. It might have actually thrown an exception while you were trying to check the predicate. This is also going to end you in the violation handler, but you can distinguish this case. And you can then even get that exception out. What's the current exception? You have this other enum here, which contract semantic you're currently using. This is something you're going to be talking about in a minute. There's 2 options here, enforce and observe. There's a few more. Going to have a slide on that in a few minutes. And the last one is the assertion kind, which is just a syntactic, which syntactic assertion kind failed. Was it a pre, post, or a contract assert? Unfortunately, we can't use contract assert here because contract assert has to be a full keyword. So pre and post are contextual keywords, so you can still have a variable named pre or post. It's not going to break. Contract assert has to be a full keyword because otherwise, you have to be able to disambiguate it from a function call or a macro call, right? So that's why we can't use contract assert as an enum here because it's a full keyword. So we just use assert. So it's a bit weird, but assert means contract assert. And then we have this function that we already talked about. This is all the library API there is. You only really needed to implement a contract violation handler. It's all in namespace contracts. It's all in header contracts. And you don't need this header to write pre-post or contract assert. So 99% of developers will never need this header. The only person who needs this header is the person who implements the contract violation handler. And that's going to be probably 1 person per company, right? Because it's a link time thing. So we're almost done with kind of what's in the proposal. There's one more aspect which is quite important, which is the semantics, which I talked about a little bit already just now. So we have these 3 roles, right? We have somebody who is using the function, somebody who's implementing the function. They need to talk to each other about, they have a contract between each other, right? The pre and post conditions. And then there is this third role of the person who compiles and links the program and who decides whether the checks are enabled or disabled, whether the contract violation handler is there and what it does. So there's this enabling configuration stuff, and how does that actually happen? So there's one thing we already saw, which is the violation handler. There's another aspect, which is, are the contract checks even on, and how are they checked? And this is the last piece of the puzzle here. It's called evaluation semantics. So you have a choice between 4 evaluation semantics on this proposal. The first one is ignore, which is pretty much equivalent to cassert ndebug is on, except that you're actually still parsing the code. So it means don't do anything. Don't check the predicate. Don't evaluate anything. Just compile it out, except it's still parsed. So that's what you do if you don't want to spend any cycles on checking any of your contracts because you know that your program is correct for whatever reason. Then there's observe, which is a little bit more than that. It does check the predicate, and if the predicate fails, it calls the contract violation handler. But when the contract violation handler returns, it just continues execution. And that is useful, for example, if you have a pre-existing code base, and you don't want to, like, you want to add contract assertions to this existing code base, but you don't want to take down the entire production system if one of them fails, because you kind of know it's been running for the last 10 years. It's probably fine, but you want to know if there's a violation, but you don't want to take down the entire system. So this is when you use observe. And you can do tricks like a contract violation handler that is only going to log like a certain amount of contract violations so that you don't get like gigantic log files or whatever. So there's lots of stuff you can do there depending on what you want. Then there's the enforce semantic, which is the default, which is you check the contract, and if it fails, you call the contract violation handler, and if the contract violation handler returns, you terminate the program, right? So this is the default for assert, and this is also the default for contracts. And then there is a fourth semantic, which is useful when you don't want to pay for the code bloat of the contract violation handler having to create this contract violation object and pass it in. That's a lot of like, there's like 5 members in there or something. You don't want to pay for that code bloat. And also in a, for example, in a safety and security context where you just want to, if something went wrong, you just want to terminate the program as quickly as possible. Not call into any functions, not do anything else, just trap immediately. This is something you typically do in a safety critical context. And for that, we have the fourth semantic, which is called quick enforce, which checks the predicate. If that doesn't evaluate to true, it just immediately terminates the program. No contract violation and then nothing. And so there is actually a fifth semantic, which is kind of conceptually there, which is the assume semantic, which is you don't check the predicate, but you optimize on the assumption that it's true. This is what the assume attribute does in C++23 today. So you can also do the same thing with contract assertions. However, it does introduce additional undefined behavior to your program if your contract assertion is violated. So it's kind of like, we're not sure yet how this fits into the whole picture with safety, security, undefined behavior. So we decided to leave this semantic out of the initial version of this proposal. So the initial version of this proposal only has these 4 semantics. The 5th one we might add later once we're sure what the consequences of doing that will be, because it's very, very, very handy to squeeze more performance out of your code. But there's a trade-off that we need to discuss before we add this to the proposal. In the kind of context of safety and security is very important. You need to make sure that this is the right thing to do, so we leave it out for now. So how do you choose this semantic? Well, the proposal doesn't really say. We leave that decision up to the compilers and the tools, but you want to make sure that we support every possible scenario that we're aware of. So the most common one probably will be to choose the semantic at compile time. So there's going to be some kind of compiler flag for that, which the proposal doesn't specify compiler flags, but that's what we expect compilers to offer. You could also presumably choose the semantic at load time, at link time, at runtime. There's lots of different scenarios here that are possible. For example, you could enable assertions when you attach a debugger at runtime. That is a perfectly valid implementation of this proposal, and maybe tools want to do something like this, maybe not. But we think it's useful to specify it in a way that it allows all of these scenarios. There's a paper here, P3321, which talks a little bit more about what we actually expect compilers to do, what options and flags we actually expect them to offer. So this choice of semantic can be the same for all contract assertions and translation unit. That's the typical choice, what you do with CAssert today. So certainly we want to support that, but we can also do more interesting things. So each contract assertion can have a different semantic. You could only check pre and not post, right? That should be allowed. If a compiler wants to offer a flag to let you do that, that should be valid C++, so be specified accordingly. You could also want to just check a random subset or check an evaluation every 10th time. So you can't even assume that the same contract assertion will have the same semantic every time it's going to be evaluated. You can do very interesting things here. You could we also allow evaluation to happen twice. For example, if you have one translation unit where you have, which is compiled with callee side checks enabled, and another translation unit which is compiled with caller side checks enabled, where you could presumably check on both sides, and you want to link them together, you might end up with checking the same assertion twice. That's valid. Or the compiler can also look at the assertion and say, well, I kind of know that this is going to be true. I can reason about that. I'm not going to bother evaluating the predicate. I'm just going to elide it. Like you can elide, for example, a copy elision or something like this. So this is all allowed. This is kind of very flexible. There's one consequence of this, which means you can't really rely on any side effects in the predicate actually happening. This is a really important difference between P2900 and macro assert. So with macro assert, you can have something like this, where, for example, you have an assertion that you don't iterate more than n times or whatever, and you keep state inside the contract assertion. And you know that at least within one translation unit, like it's always either going to be on or off. You can kind of rely on that. That doesn't work with P2900. If you do this, it's going to compile, but you don't have any guarantee that that increment is actually going to happen once exactly every time, because you don't know what the context semantic is. That's unknowable at compile time. You can't rely on this. You also can't currently have like something like a variable n iter, which is only defined if contract checks are on. That's another feature we don't have yet. We might add that after this initial version. So what you have to do to fix this here is you have to move the modification out of the assertion. So the assertion can't actually change any state. It can only check state, right? This is one manifestation of our most important design principle that is behind this proposal, which we call the context time directive, which is the presence or evaluation of a context assertion in a program should not alter the correctness of the program. And we enforce this at compile time to the extent possible. So we specify it in a way that if you add pre and post to a function that you already have, that's not going to change overload resolution. It's not going to change concepts. You can't sphere on that. It's not going to modify what your program does. And also, if you don't check the assertion, it's not going to do any extra stuff. It's only going to do extra stuff if you actually turn it on. So if you just add pre and post and context assert to your code, it's not going to modify the program in ways other than checking the predicate. There's one case where we can't really enforce this at compile time, which is the side effect case that we just saw, right? So we can't really make side effects ill-formed, because deciding whether a function has side effects is basically the halting problem. And reducing the allowed expressions to a subset where we can prove that they have no side effects would basically make this feature unusable, because you could only write the most simple expressions. You couldn't even call vector size, for example. Which you kind of want to do in a contract. So what we do instead is just don't use predicates with side effects that could, modify your program, or whether any other assertions return true or false, which is basically, I think, the most simple way to put this is maybe just don't use predicates with side effects at all, unless you're really sure what you're doing and you're really sure that it's okay if those side effects don't happen. For example, one valid use case would be you want to check a variable in your predicate which is concurrently accessed by other threads, so you can put a lock around it or something like this, right? So that's probably going to be a side effect that's not going to mess with other things, although that depends on your program. So the kind of basic rule is maybe just don't use predicates with side effects at all. And if you stick to that rule, you get one really important benefit is you can't get Heisenbugs, so-called Heisenbugs, which you can get with macro assert, but you can't get them with P900. That's a situation where you have a bug, you add an assertion, and then the bug is gone. And you remove the assertion that you put there to find the bug, and then the bug is back, right? So that can happen with macros. It can't really happen with this proposal, so that's a big benefit. Okay, one last thing is in the last revision of this proposal, which came out of the last committee meeting in St. Louis back in June this year, we added a new feature which people were asking for, which is virtual function support. It was missing until then, and people were saying, well, that's not good. You want to add pre and post conditions on virtual functions. So you kind of have to figure out how to do that, and we did. So that's now in the paper. Notably, we are not doing it in the same way that Ada, Eiffel, and D are doing it. So they are doing it in this classic Bertrand-Meyer style. You can only widen preconditions and narrow postconditions. And that works really, really well as long as you stick to classic by-the-book object-oriented programming like you do in Java, for example, or other languages like that, then that works. But if you do more interesting things with virtual functions, which you can do with C++, like you can do type erasure, or there's multiple inheritance also, and that paradigm doesn't really work with any of those more interesting scenarios. So we came up with a specification that actually works for C++. This is the mental model behind it. Lisa, thank you very much for that diagram. I think you're going to be talking more about this in your talk tomorrow at the same time. So we have this mental model that if we have an indirect call, like a virtual function, for example, then we have a caller-facing contract and a callee-facing contract. And we want to check both of them, right? So we check the preconditions that the caller sees, then the ones of the callee, the implementation, then we execute the implementation of function. Then we call those postconditions, and finally we call the postconditions of that the caller sees. And for a virtual function call, the left-hand side is the pre and post on the function that you called. And the right-hand side is the pre and post on a function that ended up actually running, that was selected by the V table, right? And so you want to check the pre and post conditions of exactly both of those functions. So here's an example. We have, for example, a unary function, which has a virtual function compute, and it has a precondition that you have one argument. And then you have a binary function, which has a precondition that you have two arguments, right? And what you can now do with our proposal, which you cannot do with, I think, in any other language that supports contracts, is you can inherit from both of them, and then you can have a variadic function which has no preconditions, and that's fine. And it depends on how you call it and what function ends up being called. For example, if you have a variadic function, you just call that variadic function class, and you statically know it's a variadic function. Then you can call it with 1, 2, 3 arguments, no preconditions are being violated, except the ones of the actual function, which if there were any, they would be checked, but there are none, so you're good. But if you call the same object, which is a variadic function object, through a reference to unary function, then you additionally check the pre and post conditions of unary functions. So if you pass then more than one argument, you get a contract violation because you used the interface incorrectly, even though the underlying object might do what you want, but you don't know at compile time whether that's the case. You only see the interface. You need to call the interface correctly. And the same if you use that same object through a binary function reference, then you're going to get the preconditions of binary function called. So it depends on how you use it and depends on what you end up calling. And both of those contracts need to be satisfied. And it turns out that's exactly the set of contracts that you need to check to make sure that nothing went wrong. Like notably, if you have, for example, an intermediate class, you inherit from A, B inherits from A, and C inherits from B, and then you call a C through A, you're not going to check the contracts of B. B is irrelevant here because you're not calling B, you're not end up calling B, you're not using B, it's irrelevant. So you check exactly those four contracts here, which is exactly what you need to do, because this one catches bugs because you used the interface incorrectly. This one catches bugs in your implementation. Like if you implemented the function wrong, it doesn't satisfy its own post conditions. And these other two catch bugs where basically you didn't use inheritance properly, and your derived class isn't actually fully substitutable for the base class, and you messed that up. And that's what these are going to catch. So you catch exactly the things that you want to catch if you want to know if you have a bug in your inheritance hierarchy. So this is all explained in this paper P3097, and I think Lisa might want to talk more about this and other aspects of contracts in her talk tomorrow, I think also at 2 p.m. So go to that talk, that's going to be great. We have a few minutes left, so I quickly want to talk about some remaining open questions that we haven't figured out yet. And as soon as we figured that out, we're going to be done with this proposal. One is, you want to make pre and post work on coroutines, which currently doesn't work, but we already know how to do this. Like we made very good progress on this just in the last few weeks. We figured it out. I mean, there is a paper that figured it out already last year, but now we actually convinced ourselves that that solution was correct. So we kind of know how to do it, but we haven't approved that solution yet. So I'm not going to talk about this now. It's not official yet. This is a work in progress. We might want to make pre and post work on function pointers. So you might want to do this, something like this, which kind of fits into this mental model, right? You have caller and callee. In this case, pre and post on a pointer is the caller, and pre and post on a function that's being pointed to is the callee. Turns out it's actually really tricky to make that work, because if you put this on a pointer, the information that the contract is there needs to live somewhere. Where do you put it? Do you put it as part of the type? That breaks a bunch of stuff. Do you put it in the pointer value? It doesn't quite work. Where else do you put it? You can make it a property of the declaration, a bit like a line as or something. It's not really part of the type or the value, but the compiler kind of knows about it. And that seems to be kind of a viable strategy, but there's still something missing there. We can't quite make that work in all cases. So we are missing a feature here, which we haven't had yet. And there is a paper by Lisa here talking about one way of achieving that. There might be other ways, we don't know yet, but this is going to be the subject of ongoing research. This is not going to be in C++26 because that is surprisingly tricky to figure that out. Another open question is this thing that we have called constification, which we are not sure yet if we want to keep that around or not. It's this thing that in a pre-post or contract assert, local variables are implicitly const. So if you're trying to increment, for example, a parameter, you're going to get a compiler error. It's like as if you were in a const member function. It's not going to let you do that, which is great because you shouldn't be modifying your program. You should only be checking if your program is correct. Remember the prime directive. So it's a good thing that you get an error there. But there's a few problems. For example, if you have a predicate, but you forgot to put const on it, then that's not going to compile. You might want to work around that with a const cast, but maybe you can't do that because it's not your code or because const cast is just horrible and ugly and we don't want to use that. So we might just say, let's not do this, and it's just an expression, and there's some pros and some cons. I don't really have time to talk about this in much detail now, but it's like, yeah, we can do the constification and not do it, and kind of both approaches are kind of right in their own way. It's like a trade-off. We're not sure what the right solution is. We're currently kind of split on this issue. We need to figure this out before we can ship this proposal. Another open question currently is, how do we deal with undefined behavior in a predicate? An example here from a paper by Gabriel dos Reis is you have a function that adds two integers, okay? And the compiler can assume that this never overflows because this would be undefined behavior. This is how undefined behavior works. You can assume it never happens. And then it turns out that, well, that means that f will always return true, right? So the compiler will replace f with true and basically then replace the entire thing with pre-true and just compile out the entire contract assertion, even if it's enforced. So that's a bit scary, right? The problem, though, is that this is just how expressions in C++ work, right? Overflow, integer overflow is undefined behavior. This is just the semantics of the language. And we don't really want to mess with that either. So this is probably not much we can do about that because we would have to redefine how expressions work in contracts to do anything here, but like we don't really want to change the semantics of the language here. So this is another thing that we have ongoing discussions about how to deal with this. And finally, the last kind of open question is, does this actually work? Like, can you actually implement this? And this is also work in progress. We have now people working on both GCC and a Clang implementation of this paper. Hopefully soon there will be something public to share, certainly before this proposal gets into C++26. We have a few extensions that we might want to consider. Post-MVP, post-26. One really important one is so you can talk about old values. You can say, for example, in the post condition, the size has increased by 1 compared to the size that it had before when the function was called. We don't really have a syntax in the paper to do this, but we came up with this capture syntax like lambdas, with which we can express this. But this is going to be a post-MVP feature. This is not going to be 26. There's a few other features that we already know we're also not going to get in CPlusPlus26, or at least in this first version of the proposal. But we expect to be working on more and come back to that after CPlusPlus26, and then hopefully add that at some point in the future. Right, and now I have 3 minutes left, so I can talk about another aspect of what contracts are for, which has been quite an active discussion also this week. People have asked, well, are contracts a solution to safety and security in C++? This is obviously the hot topic right now. And it is an interesting question. I think it's very worth thinking about this a little bit. So I hope I convinced you that contract assertions can significantly improve correctness and safety of code, right? So if you have something like op8 square bracket, which can have undefined behavior, you put a precondition on it, you enable the check, you no longer have undefined behavior. Your code is more correct, safer. It's great, right? But you actually have to put the assertion there. Like if you don't put it there, it's not there, right? And it turns out you can't always do that. Like there are contracts which you can check easily with a contract assertion, like this one. It's straightforward. There are other cases where you can check a contract with a contract assertion, but it's going to cost you. For example, binary search is O log n. It has a precondition that the range is sorted. And you can check that precondition, but checking that precondition is ON. So by checking the precondition, you would actually violate another precondition or another contract of this function that is ON, O log n, right? So you probably don't want to enable this in your code unless you have some kind of super careful mode that can be very slow or something like this. And there are also cases where you just can't write a predicate at all to check the contract. For example, the contract is that the pointer that you pass in points to a valid object. That's the classic problem that memory safety features that address memory safety are trying to solve. Contracts don't really let you do that. There is no way to express in a Boolean C++ expression, this pointer points to an existing object. You can check if it's not null, but that's only half of the problem, right? But like contracts don't give you a tool to do that. They just give you a tool to write an expression and then check it. But they don't solve this particular problem. Or for example, this function will return a value. That's the halting problem. You can't solve that with any expression that you might write. So there are contracts that you cannot verify with contract assertions. So contract assertion can detect if a contract is violated, but they cannot prove that no contract was violated because there's always going to be a part of the contract that you cannot express in code. You can only express a subset in code. So you can't really use it for correctness proofs in that way. And the other thing is that they only check for correctness during evaluation of the program, right? So that includes constant evaluation. That was a question earlier. So if you have a function with a precondition you evaluate it at compile time like this, you will get a contract violation at compile time, which is just a compiler error if you turn them on. So that works. But what it doesn't do, it doesn't give you new language constraints. It doesn't give you new language guarantees. And therefore, it doesn't also give you guaranteed memory safety. But there are other approaches. How we get there, we talked about this in other sessions this week. There is work on to add a borrow checker to C++. There's erroneous values, which are no longer undefined behavior. All of the stuff that changes the semantics of the language and adds new guarantees to the language. So contracts don't do that, but they complement those features because everything that those new features didn't catch, you can then catch when you actually run your program with contracts. So it's kind of a complementary feature to this other stuff. So I think this is kind of the purpose of contracts, and I hope you found that helpful and interesting, and thank you very much for listening. You probably don't have time for questions, or?
How the propagation of contract violation will work? Are you going like to an empty stack to find the handler for it, or you will have some like kind of direct connection into handler?
I'm not sure I understand the question.
So like if the contract violation happens,
yeah.
So it's like kind of exception.
Yes.
You need to find the handler.
Yeah.
How this will work?
I mean, it's just a function. It's like a symbol in your program. You call it.
Okay, but did you consider something like exception propagation? So I mean, like going through the stack, and like in this case, it will be possible to add custom handlers, not the single one for the whole application.
I mean, you can write a single handler and then dispatch to other functions. You can do that. But I don't see what you mean by going through the stack, because you evaluate an expression. If that's false or throws, you immediately go to the violation handler.
I see.
So there isn't really a stack to go through. You just call the violation. It's like a function call that the compiler generates. And then in there, you can do whatever you want. You can dispatch to different other handlers or whatever, but you have to write that yourself.
So yeah, I understood. Like you have direct connection to this function.
Yeah, it's like, I don't know, like you try to throw through a no except boundary, and then the terminate is going to get called. And that call, the compiler just generates for you. But there's nothing else to do. It's just you call that function. That's what happens. It's like that.
Yeah, got it. Thank you.
We only have a short break until the next one.
Okay, so maybe we should then end this official session and then just answer questions just informally by standing around here.